Okay, we're going to take a look at how calculus can help you understand motion. And physics people, you may know some of this already because calculus, physics, and motion are all intertwined. You also know by looking at the length of this video that it's going to be a long one, but do not despair. The actual knowledge is pretty easy. There's just a lot of individual things to put into your brain, but none of it is too difficult. To begin with, I'm going to start off with just an intuitive example so you understand how the AP likes to look at a problem with motion. Very frequently, they will talk about an object that is traveling left and right above a horizontal axis. So here's a horizontal axis, and imagine that the object, they usually call it a particle, is just going traveling to the left and the right, and you can mark its location. So for example, right here, this particle would be at a location of 8 meters to the right of the origin. So if that was confusing to you, it won't be when we go through this. I have already given us a position function, a velocity function, and an acceleration of some particle. So, for example, if I wanted to know what is the position of my object at time 0, I plug in a 0 into here, and I've done all the math for you already. At time 0, its position is 2. That means its location is 2 when it starts. By the time I get 1 second in, it's already at a location of 10.3. So it went from here all the way over to here. This is where it is at time 1. This is where it was at time 0. And now I can just keep doing that. By the time I get to second 2, it's at 12.7. So now it's at time 2. And then I'm just going to continue to fill these out. You can see that. It goes back to 11, then 7.3, 3.7. What I've done is I've filled in all the locations, and if you kind of draw a little map of what this little particle was doing, it was traveling to the right, and then somewhere in there it decided to turn around, and it's traveling to the left, and then it turned around again. And it ended up right there at t equals 8. So you see what this little particle is doing, just cruising around, traveling to the left and the right above a horizontal axis. I got all those locations by plugging into the position function. So that's usually the framework that the AP is going to ask you motion questions. They will vary from it, but you have to understand that style. And the types of questions they will ask are, what is the position, or is the object traveling to the left or the right at time t equals 5, or what's the nature of the speed, is it speeding up and slowing down? So now what I would like to do is move on to the 5 items that you need to make sure you know by the end of this video. And here they are. You may want to copy these down. But we're going to go through all 5 of these. I'm not going to read them to you right now. But these are the fundamentals that you need to know about motion. And if you know these, you are pretty much bulletproof on most motion questions. Okay, I'm going to address the first item on the list of things you should know, which is there is a derivative relationship between position and velocity and acceleration. You maybe noticed it when I put up these functions in the beginning, that these are derivatives of each other. If you didn't notice it, no big deal, but you're about to see it. If I have a position function, in this case it's a very friendly power rule problem, I can do the derivative and get the velocity function. And once I have a velocity function, I can do its derivative to get the acceleration function. So it's a very easy derivative relationship. And here it was in practice, but you can also show it with math symbolism. Velocity is the derivative of position. Acceleration is the derivative of velocity, or the second derivative of position. So in a situation like this, if I were given a position function and they asked me about the velocity, I would simply say this: v of 5, they want our velocity at time 5, is equal to the derivative of position at 5. So in this case, I already have it up here, but let's say I didn't have that. I would go ahead and find the derivative of position, and let's just do this. And if you go ahead and do the mental math on that, you can find out the velocity at time 5, and I think it's 25 minus 40. This thing ends up equaling 3. So I could just say v of 5 equals 3 meters per second. I haven't been very clear with units. We'll just say we're using meters and seconds for units because that's what all the cool physics people like to use. So item number 1, there's a derivative relationship. It's very straightforward. Let's move on to the second item you need to know, which is the direction of travel. Okay, so the direction of travel, we know that our little particle, especially from that opening example, the particle is sometimes traveling to the right, and then sometimes it switches back to the left, and it might even switch back again, who knows. So it's at time traveling to the right or the left, you just don't know, but here's how you do find out. You simply look at the sign of velocity. So when a particle is traveling to the right, the velocity is positive. If a particle is traveling to the left, the velocity is negative. It's that simple. So if they say, what direction is the particle traveling at t equals 5, I would care about my velocity function. So if you look in this last example, we already worked with the velocity at t equals 5, and we decided it was, oh my, I'm going to go back here. That's supposed to be a negative 3, and a negative 3. 25 minus 40, yeah, those are negative 3s, so that's a big deal. Sorry, I hope you caught that and were saying bad things about me. I'm going to now use that item over here. At t equals 5, the velocity was negative, so the object must be traveling to the left because velocity was negative. And on an AP style test, they're not just going to want the left or the right, they're going to want a justification. They're almost always going to want justifications. My sincerest apologies for that. Why didn't you say something when I screwed that up? Alright, so now let's take a look at this one. At t equals 1, is the object traveling to the left or the right? What I would need to do is plug a 1 into v, and hopefully not screw this one up. So I get a positive 5, so the object must be traveling to the right because v of 1 is greater than 0. Notice here I say v of 1 is greater than 0. You have to be careful because if you say v of t greater than 0 in the wrong context, what you're saying here is the velocity function is always positive, and it's not always positive. It's positive at time 1. So if you use this, if you aren't very clear with your writing to say v of t is greater than 0 at t equals 1, you may end up losing a point just because you weren't precise enough. Alright, but direction of travel is easy. Just look at the sign of velocity. So let's keep on going through these different items that we need to know. We need to know when an object switches direction, or how to justify that an object switches direction. So if you remember from this opening example, and we keep using these equations, as I graphed these different positions along the way, I saw that the object changed direction, probably at t equals 2, maybe over here, I don't know, maybe t equals 6, but we don't really know for sure because there could be things happening between, say, second 5 and second 6 that we're not sure of. But we have a rough idea of when the object is changing direction. So the way to justify that an object is switching direction is simply to check to see when the velocity switch is signed. Simply put, if a velocity was positive and then it goes to a negative velocity, the object went from heading right, positive velocity, to heading left, negative velocity, so it switched direction. So here's a common student mistake. Finding the time that velocity was equal to 0 is a great place to investigate, but it's not going to be a guarantee that the object switches direction, and I'll show you why here in a little bit. But let's continue on with this velocity function that we've been using. That's the velocity function we've been using, and if I want to find out when it switches direction, the first thing that would be good to know is find out when does it equal 0. So in this very friendly case, I do the good old algebra 1 factoring, and I solve, and I find out at t equals 2 and t equals 6, my velocity is 0. Now I have to have some math sense about me. If I take a look at this is a parabola opening upward with those x-intercepts. So I know that the vertex is between there. So the vertex is going to be somewhere down here. So by just knowing the nature of this graph, I can tell that the graph has that rough shape. So I now see at time t equals 2, the velocity went from positive velocity to negative velocity. The object switched direction. At t equals 6, the velocity was negative just before t equals 6 and positive just after t equals 6. So I can simply say this: the object switches direction because velocity switches sign. Now, I chose a very friendly example. The times that led to a velocity of 0 ended up being a switch in the velocity sign, so a switch in direction. But remember, you can run into functions that look like this. What if you had a velocity function that was going la da 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 da? So at that time, let's just say this is t equals 7. The velocity is equal to 0, but that doesn't mean the object switches direction, because what if the velocity decides to go back like that? The velocity was positive just before t equals 7, so the object was traveling to the right. And then just after t equals 7, the velocity was positive again, so the object continues to travel to the right. So in a case like this, velocity equals 0 was a good place to investigate, but because velocity didn't switch sign, we don't get a change of direction. Okay, I had an interruption, so now I have to, it was pretty lengthy, so now I have to try to remember where we were. I think we're done with switching direction. We were going to now look at speeding up and slowing down, which is item number 4 on the items to know for motion. So, remember, as this particle was traveling to the right and traveling to the left and switching direction and doing all that stuff, there were times that its speed was increasing and there's times that its speed was decreasing or slowing down. So here's what you're going to need to memorize. A particle is speeding up if the velocity and the acceleration share the same sign. And a particle is slowing down if velocity and acceleration have opposite signs. Now I know in physics there's another way to justify that, and it's totally a solid justification. Unfortunately, on the AP Calculus test, they're going to require that you use this for your justifying. So if I look at time t equals 5, and I'm going to go back to the original scenario, at time t equals 5, let's see, 0, 1, 2, 3, 4, 5, that's where we are at times t equals 5. The object is traveling to the left, and we're wondering if it's speeding up or slowing down. So if I look at this chart, handy-dandy chart I made in the beginning, at t equals 5, the velocity is negative because it's traveling to the left. The acceleration is positive. That tells you, since velocity and acceleration have opposite signs, the particle is slowing down. And there we write it up. The object is slowing down because velocity and acceleration at t equals 5 have opposite signs. If I look at time t equals 3, which is going to be our next question, at time 3, the velocity is negative, so it's traveling to the left. Acceleration is negative. Velocity and acceleration share the same sign. So the object at t equals 3 is speeding up. I just wrote it a different way because velocity is negative and acceleration is negative. And just as a side note, I can also say it's traveling to the left because velocity is negative. Speeding up and slowing down is as straightforward as just comparing your signs of velocity and acceleration. We have one more item to go, and on the items to know, it's displacement versus distance traveled, and then as we do that, I'm also going to talk a little bit about speed versus velocity. Okay. So the last item, I'm making up a new example, so you can kind of ditch the old examples for a while. And I have we don't know the equations, but we know these are the positions at various times. So at time 0, at time 0, the location is 5. And then it moves to location 10, then location 15, and then it zips around backwards back to location 5, then all the way to -5, -10, and then it zips back to location 0. So that's where my particle is traveling. And so now if I want to know the displacement from t equals 1 to t equals 2, I simply think about this idea. Displacement is change in position. So at time 1, it's at position 10. At time 2, it's at position 15. So the displacement is positive 5 meters. The positive tells me that during that time, from time 1 to time 2, it moved in the right or positive direction, and it changed position by 5 meters. If I think about displacement from 2 to 4, here's time t equals 2, here's time t equals 4. So it went from a position of 15 all the way to a position of -5. This tells me that my change in position is negative because it ended up way left of where it started. If it started at 15, ended at -5, it has a displacement of -20 meters. The positive minus sign is important. Now let's think about this for a second. If I asked for distance, so let's go back to this first one, from time 1 to time 2, it went from 10 to 15. It traveled 5 meters. Distance never has a positive or a negative because you can't have a negative distance. Nobody runs the negative 100-yard dash or the negative 26.2-mile race. So distance and displacement in this case were the same, but in this one, my displacement was negative 20 meters, meaning I finished 20 meters left of where I started. But my distance, I went from here, 15, all the way to here, negative 5. That's a distance of 20 meters. Notice that I don't have a negative sign on there. So displacement always has a plus or a minus. Distance is always a positive answer. All right, let's look at this final one. The displacement from t equals 4 to t equals 6. At t equals 4, I was at negative 5. And at t equals 6, I'm back at 0. Now during that time, I traveled to the left, and then I went back and traveled to the right. But displacement doesn't care. Displacement only cares about change of position. So in this case, I just look at the beginning location and the ending location. I was at negative 5. I ended at 0, which means I have a shift in position or a change in position of 5 meters. And it's positive because I end up going to the right or ending right of where I started. If I did distance in this case, I would say I went 5 units, then I switched direction and went 10 units. So that distance is 15 meters. So that took a little bit of thinking there. It wasn't as easy as figuring out the displacement. So be careful knowing that distance is always positive, displacement is a positive or a negative, and distance and displacement are not always the same value. So you have to be very careful with that. In a related example, know that speed, how fast an object is traveling, is the absolute value of velocity. So what do I mean by that? If my velocity of an object is, say, negative 18 meters per second, that means the speed is 18 meters per second. The negative on velocity just tells me I'm traveling to the left. This is my speed. If I said a velocity of an object is 23 meters per second, well, now it's traveling to the right because there's no negative sign. The speed is also 23 meters per second. So velocity and speed have this unique relationship where sometimes they're the same, sometimes they have opposite signs. A similar phenomenon happens with distance versus displacement. All right, this was a lot. Thanks for hanging in there. But now, in theory, you know all the fundamentals of motion. They're not too difficult. There's just a lot to install into your brain.